In this session, we will discuss about chemical equilibrium. Chemical equilibrium has to do with reversible reactions. Reversible reactions meaning that the reactions can go both ways to the product side and also to the reactant side. Suppose we have a reaction of A plus B forming 2C plus D. Let's make this 2A. Now, normally, what we know from the previous chapters is that A and B will combine together to form C and D. And then at some point after the reaction is finished, either one of the A and B or both of them will be consumed completely. And therefore, you recognize the terms of limiting reactant and so on. Now, in the case of chemical equilibrium where we have reversible reactions, we do not have any limiting reactants. And in this case, because you can see that the arrows go both ways, it could be forming the product and also forming the reactant. There's no guarantee that the reactant is being consumed and the product is being produced. It could also be that the reactant is the one that being formed and the product is the one that being consumed and the arrow goes that side. So how do we determine whether the reactant is being consumed or the reactant is being produced? We will learn about that in a bit. But still, it is noteworthy that we still call A and B reactants and C and D products, even though A and B will be produced and C and D will be consumed. We still, once more, call AB as the reactant and CD as the product. Now, in the case of chemical equilibrium, we also recognize this term of a constant of the equilibrium. So we have K over here. Now, the way we calculate K, we can classify into two different methods, which is Kc and Kp. So Kc is based on concentration, so what we will see is molarity of each of the products and the reactants. And in this case, we can see that we only take the reactants and products whose phase is either aqueous or gas. On the other hand, for Kp, P stands for pressure, so we only take the pressure, which is in atm, and therefore we only take the gas molecule. The mathematical expression for K is as the following. First, we have to decide the phase for our imaginary reaction. Say we have here aqueous and then gas, and then here aqueous again and then gas, just for the sake of it. So Kc is the product, concentration of each of the product, power to the coefficient. So here coefficient plays very important role. So make sure you have a balanced reaction before you start writing the mathematical expression. And then divided by reactant, also power to its coefficient. So 2, and for B it's 1. Now see that for Kc we use everything because here we have aqueous, gas, aqueous and gas, so we use everything in our mathematical expression. However, for Kp, we only use the gas phase. And therefore, here we can write down that Kp is equal to the pressure of D, partial pressure of D, divided by partial pressure of B. Also power to each of their coefficient. And in this case, because it's both 1, they're both 1, so this one power to first, this one also power to first. Or you can also not write them. However, in case of this having coefficient that is not 1, for instance 3 or so, then you have to power this to the third or other power this to the third or other different values. Okay? So what does this mathematical expression tells us? If we try to monitor this reaction, let's write a plot of Let's draw a plot of this reaction. So here is the progress of the reaction. And this one is either the molarity or the pressure. So a way to express the amount of these products and reactants. So in the beginning we have a certain molarity of A, and then at some point if the A is being consumed, it will decrease and becoming like that. Likewise for B, it's like that. And for C and D, for instance, in the beginning we don't have any C, so it starts here and then it goes up. So this is C, this is A, and this is B. And D, say that we start with some amount of D. So it's not zero. Yeah, we can start, for instance, here. D will also go up like that. Now, what we call the equilibrium condition is when this situation is reached. So there is no more change macroscopically for either A, B, C, or D. So what you see macroscopically is a constant process. There is no more addition of A or addition of D. There is no more consumption of B or addition of C, and so on and so forth. This is what we call when it reaches the equilibrium. And that particular equilibrium, we can find that the ratio of the product powered to each of the coefficients divided by the concentration of the reactants powered to each of the coefficient will be a constant, and that is the Kc. From this point on, I want you to remember that the only thing that changed the K, the only thing changing the K is the temperature. I want you to remember this very carefully. Because at some point we will discuss about the shifting of this equilibrium. It can shift to the right or to the left, to the product side or to the reactant side. However, the shifting will not cause changing of K, either Kc or Kp. The only thing that changes the K is the temperature. And also, which is why in some of the experiments, you will also see the temperature defined in the chemical equilibrium problems, because if we change the temperature, we will also change the K. Although macroscopically we see no more change for the reactions when they reached the equilibrium, dynamically actually the microscopic scale reactions still happen. So A and B still form C and D. C and D also still form A and B. However, the rate to the right side and the rate to the left side are perfectly equal, and therefore we see no more change at the macroscopic scale.